So we move on to another key component of the warm coast field effort, as we've seen before, Sebastian in representation of the southern part of the Atlantic, but in representation of our American collaborators from the US mostly, Alex Sims, who is going to be talking not about the US, but about what do we know about relative sea level changes in Antarctica, MIS 5E relative sea levels in Antarctica. So this is a talk I'm looking forward to hear, and not only me, I guess. Thank you, Alex.
Thank you. I don't think I've ever given a talk in a room where there's some creepy faces looking down at me, but this is kind of cool. And thank you, Alessio, for all the work and for letting us all get together to discuss these really interesting stuff that's going on. And before I get started, I'd like to acknowledge my co-authors on this. Sarah Bradley did some of the GIA modeling that you'll see at the end of this talk. Teiki, Dominic, Toru all helped as they've been to some of the other areas in Antarctica that I'll be discussing today. And Jeannie DeWitt is my collaborator who knows all things OSL, and I'm grateful for her. So I'd like to acknowledge them before I get started and speak on their behalf. Hopefully they won't be too upset with what I say. So I feel like I'm kind of speaking to the choir here, but why are we all interested in these sort of last interglacial sea levels, right? I think one of the big selling points is, it's MIS 5E or the LIG, whatever we want to call it, is possibly an analog for what we are looking at and staring down in the future. But as Andrea and kind of went over, and Alessio already mentioned this morning, there are still some pretty major unanswered questions about sea levels during MIS 5E. What was global mean sea level during the last interglacial? That traditional view of 6 to 9 meters versus there's some indications or some assertions that maybe it was less, right? What was the character of sea level during the LIG? Was it that traditional one peak? Were there multiple peaks, sort of oscillations? Were those driven by ice sheet behavior, or were those driven more by maybe some GIA components? And then an abrupt rise in the middle of MIS 5E. These are all sort of outstanding questions that hopefully some of you all will be able to answer, because I'm not going to be able to with the data from Antarctica. So an answer to all of these questions relies knowing the source of higher sea levels during the last interglacials. And, we know that there's some sort of minor, it's been estimated about 0.5 meter of sea level rise during the LIG was a result of just warming of the sea surface temperatures at that time. But that's still a minor component, particularly if we're looking at more 6 to 9 meters. And so then that gives us to the two major potential sources of meltwater, although we've heard this morning that maybe the Laurentide also, played a little different role in that extra sea level. And those are Greenland and Antarctica. And one thing, as a grad student, I remember that always kind of bothered me. When in grad school, chapter of my dissertation, we worked a little bit on meltwater pulse 1A. But the thing that always bugged me is people would go collect data from Greenland, and they would write up all this data, and they'd say the conclusion was, no, it didn't come from Greenland, it had to come from Antarctica. Or vice versa. They would write a paper about data collected from Antarctica, and their main conclusion would be about the other pole, right? And so, as we discussed, Antarctica's been discussed a lot here, but that data has not been collected in Antarctica. So what does Antarctica say about its potential contributions to sea levels during the last interglacial? And so a couple things we know. There probably wasn't, if we look at the Antarctic ice sheet, you got two big ones. You've got, you could call the Antarctic Peninsula its own little separate thing, but you've got East Antarctica, which is very high and very dry. There's some indications that maybe some of the little subbasins, like the Wilkes subbasins, potentially contributed. But the thing I always teach students is, the average temperature in East Antarctica is -60 degrees, right, Celsius. So if you warm it by 2 degrees, it's not going to do much in terms of melting, right? In fact, today we actually see East Antarctica growing because the warming is heightening the hydrological cycle and potentially even more precipitation, so it's actually growing. So the real, potential source is likely West Antarctica. And if we look at there's been attempts to directly see, did that ice sheet exist, right? And right now we have some drilling campaigns with, some logistical issues and so forth to see if we can directly date ice from marine isotope stage 5e. There was a really neat paper that's already been mentioned this morning on octopus evolution that kind of suggests, if you look at the DNA, that there had to be an open connection between the Ross Sea and the Weddell Sea. There were some early indications of some diatoms that suggested open sea ice in the early 90s, but that day, was a little inconclusive. And then there's some offshore cores with some other similar things. But we don't have any good concrete evidence one way or another for West Antarctica yet. There are attempts right now out there. But one of the ways, and hence the warm coast that we can do, is look at these sort of sea level fingerprints. And here's an example from a recent paper by Barnett, where they do the GIA model and see where the differences lie. And obviously, there's data collected from different places, but the largest sea level fingerprint for a West Antarctic source is likely going to be in Antarctica, right? So, what is the record, if any record, of last interglacial sea levels? If you're jet lagged and you're like me and you sleep through my talk, okay, hopefully I don't sleep through my talk, but if you do, just know we don't know a lot about last interglacial sea levels in Antarctica. But let's survey, and that's what I'll hope to do this afternoon, what we do know. And then at the end, I'm going to use some simple GIA models to maybe pontificate what some of these results mean. So I started by, did I skip something? Yes. Oh, no, I didn't. Okay, great. So what are our potential relative sea level indicators from Antarctica? Well, the two main ones that we don't have really nice corals, and we don't have marshes. There aren't marshes in Antarctica, but the two main sea level indicators that we can use from Antarctica are raised beaches, and I'll show another sort of raised marine platform, and isolation basins. Those have been the primarily types of sea level indicators that we have across Antarctica. There's some other limiting data of not much use, penguin rookeries, petrel nests, and lake basins. Most of those are terrestrial limiting data that's been found across Antarctica. And then there are a few marine limiting data as well. So one of those two is raised beaches. Here's a weird view of a raised beach right here in Antarctica. And the traditional way of sort of interpreting these from a sort of indicative meaning is that you measure the modern beach ridge and then you measure the elevation of the former one. There's some assumptions there. And then you just subtract the two there, and that's how you get your sea level change. The other type of sea level indicator that we have from across Antarctica are these little isolation basins, with the idea of these little ponds that form pretty close to sea level. They're separated by a sill over there from the open ocean, and when sea level either drops below the elevation of that sill or rises above the elevation of that sill, the sediments being deposited in that little basin change from marine to non-marine or vice versa. And then we often will use some sort of biological indicator, diatoms, forams, or anything, to find that transition in the sediments within that isolation basin. You date that transition, and that gives you the elevation in which sea level dropped or rose above the elevation of that sill. And so those are the two main types of sea level indicators that are found in and around Antarctica. Now, as with the last interglacial throughout the globe, dating is sometimes a little difficult, right? It's older than what we mostly use in quaternary sections, which is radiocarbon dating. And so we kind of turn to some other techniques. And some of those other chronologies that work well in other settings don't work as well in Antarctica, just as radiocarbon has its own problems within Antarctica. One is, the most common that we've seen this morning is uranium-thorium of corals. Well, there's been 44 uranium-thorium dates from corals in shallow marine sort of settings around Antarctica. 43 of those are Holocene. There's one reworked coral in a moraine in the Ross Sea. So that's our one U-series date from Antarctica. We can turn to optically stimulated luminescence. The difficulty there, at least in the experience we've had, is that the grains are very dim. If you look at areas where OSL works really well, let's say the Gulf of Mexico, the sands on the Gulf of Mexico were reworked, the modern from a Holocene deposit, which was then reworked from a Pleistocene deposit, which was reworked from a Miocene deposit, which is reworked. I could keep going all the way back to the Appalachian Mountains. But the point is, those sand grains have been reworked over and over again. And every reworking makes little defects that you need to capture that luminescence signal. And we're talking about Antarctica, where we don't have lots of fluvial systems. We don't have lots of longshore systems, drift system, longshore current systems that have been reworking those grains to give them those nice characteristics that we rely upon to use them as OSL. So we get lots of spurious OSL ages. Another one that maybe we could use is amino acid racemization. There aren't many good analogs, modern analogs for these to try to figure out how to interpret those. We've had big changes in past temperatures. Sometimes these have been submerged, and in Antarctica, where the air temperature is negative 60 and the water temperature is 30, I'm talking Fahrenheit, not anyway. But anyway, that makes it difficult to sort of model what those amino acid racemization ages mean, right? And one other complication, I'm going to show you many of the ages that I have that I'm going to show you are compiled. They're actually just pre-LGM ages, so they're 30 to 40,000-year-old radiocarbon ages. And so just from sort of the dating technique, there's a pretty good, I don't know what the right word is, but cautionary tale, and that is from the Vestfold Hills, which is in sort of East Antarctica, where originally there were radiocarbon ages collected in the 70s and 80s that were 20 to 40,000 years old. And so people interpreted these as sort of mid-Wisconsin ages. Then they tried some AAR, amino acid racemization, and they said that, well, they can't be that young. And then they had some thermoluminescence ages, although squirrely themselves suggested 400,000 years old. And then someone looked at the diatoms that were present within that same deposit, and it turns out that there were critters, diatoms, that went extinct during the Pliocene. So that original mid-Wisconsin beach was actually something left over from the Pliocene. So with this, you can kind of see some of the difficulties when trying to constrain past sea levels across to Antarctica. So we did a data compilation. We found 213 radiocarbon ages that are older than the LGM, so post 20,000 years old. Admittedly, we don't know, we interpret them with a grain of salt. 65 AAR ages, 19 luminescence ages, 6 electron spin resonance ages, and that one U-series age that I already said is from a reworked moraine. So where are they? This map kind of shows where we have some potential pre-LGM sea level indicators. I'm going to focus on basically 4 areas in here because I think this is where we have the best kind of knowledge about what's going on within these areas. So we'll start with the Antarctic Peninsula, the tropics of Antarctica up there, which is right beneath South America. So of the 4 areas that I talked about, this has the least constraints when it comes to age. One we reported in sort of the Wallace 2.0 paper from Calumet Bay. It was originally some OSL ages we got. There was this upper set of beach ridges that we got, like a 9,000-year-old age, and then like a 13, a 16, and a something or other else. And we said, well, we don't know what this is. Maybe it was, pre-LGM. There was a recent paper where they just went back and redated some of those higher and got some Holocene ages, which would agree more with that 9,000-year-old OSL. So even though we said maybe it was, it's now been shown to be a Holocene deposit. The other sort of pre-LGM deposits are reworked deposits down in George VI land and up in James Ross Island area. But the one area where maybe we can get some constraints on LIG sea levels are here within the South Shetland Islands. But like so many areas, it's complicated because it's the reason those islands are there. That's an active arc, and so it's undergoing tectonic uplift. So throughout the South Shetland Islands, you have these 3 sort of marine terrace levels. And they're mapped here. You can see the yellow all around there. They go from about 0 to 17 meters, and they're covered with Holocene beaches. And so we have ages from those, so we know that that platform is sort of the Holocene equivalent. Then you can see sort of the brown, that's the middle terrace, which goes from about 27 to 50 meters. And then the highest one up there, which is 85 to 102 meters. And here is a picture of those. You can see the lower Holocene ridges, that middle one, and then that upper one. The upper 2 are not dated, but we know that they predate the LGM because we have tills of that age sitting on top of them in several locations. They cut into Pliocene rocks. Now, admittedly, that's not a very good absolute chronology, but we know that it's younger than Pliocene and older than the LGM. The middle has been interpreted, or I don't know if pontificate is the right word, to be MIS S5E. But one of the complicating factors is, again, we have to correct for tectonic uplift. And so the middle terrace shoreline angle, that's what we usually use when trying to use the sea level indicator for marine terraces, is about 50 meters. As I mentioned, we have nothing independent to determine the uplift rate. And to make things even more complicated, there was a GPS campaign there to mostly look at the tectonics of that area. And the vertical uplift rate there was actually subsiding at 2.9 millimeters per year, which is hard to grasp with when we know that there's a 600-meter beach ridge that's 6 meters higher than today, and we have these uplifted marine terraces. But there's a lot going on glacial isostatically. There was the Little Ice Age may have contributed something there. We've had Holocene fluctuations, and this is an area with a really weak earth rheology, and so who knows what the ice is causing there. So if we assume that the next highest is marine isotope stage 11, that suggests an uplift rate of about 0.25 millimeters per year, which isn't unreasonable in this sort of tectonic setting. And that gives us 30 meters of uplift that suggests that MIS 5E is about 20 meters if this truly is MIS 5E. And what I want to point out, because we'll talk about this at these other sites, is the elevation there. The Holocene marine limit is about 18 meters, right? And the MIS 5E is about 20 meters, so around the same ballpark. So that's the Antarctic Peninsula right up there. Now we're going to go over to a bunch of raised beaches in Lutzow-Holm Bay. So this is arguably one of the most studied of the pre-LGM raised beaches. That's because they're prevalent throughout this area. And there are 2 main areas, the Ongol Islands up here to the north, but every way is north in Antarctica, right? And the Long Hovde Peninsula down south. And throughout this area, we have platforms at up to 35 meters, but unequivocally marine up to about 19 meters. In fact, the highest shells that have been pulled from here are at about 18 meters. The Holocene marine limit, for context, is about 16 to 17 meters high. The beaches there have two units. They have an upper regressive unit, which has shells that pull out from Holocene, and that's where we find out our Holocene data from there. And then a lower transgressive unit with lots of ages, 63 ages that date between 33 and 43,000 years old. And they're mostly from those two little mollusks. And these beaches are very fossiliferous. There's no shortage of shell material to attempt chronology. Some of them are in live position. It's clearly marine, probably a beach environment, which means it was originally probably deposited somewhere between 2 and 2 meters below. And the present elevations of those beach deposits lie between 1 and 18 meters above modern sea level. So that begs us the question, we have this big question mark about radiocarbon ages. They're near the limit of C14. Several of them are radiocarbon dead, but most of them are finite, suggest a finite age. There have been a couple attempts to try to date these with other techniques. One with AAR. They did both the Holocene ages as well as the old ages, and they can distinguish them, but there's no good analog to come up with a true numerical age. It was an attempt to do electron spin resonance dating of shells that they had already dated to be that 32 to 42. They had 6 groups, or 6 ages, 2 groups. One was 57 to 93 Ka, very helpful, right? And the other one was 190 to 253 Ka. So the authors here, although most of the people working in there have assumed that those to be stage 3, conclude that they think that these are older than stage 3. There was one other attempt recently by Toru using OSL, luminescence. And the OSL signal was too weak to use OSL, so they had to turn to IRSL. Unfortunately, the samples that they had access to, since it's not exactly easy to get to this part of Antarctica, were not the exact same unit. It was an upper unit, which had the Holocene ages in it, and then a lower sand. And in other places, that lower sand is where they were pulling out those 33 to 43,000-year-old ages. They did 7 ages from the radiocarbon dated ages. They got between 7 and 25 on the 6 to 7,000-year-old ages, and 3 ages from the lower unit, which gave much older than the stage 3. But that still begs the question, is this the same unit that those radiocarbon ages were from? So, as unsatisfying as it is, what we can say about Luton Bay is we have a marine limit of this some sort of high stand that's pre-LGM of 18 to 19 meters, lots of 30,000-year-old radiocarbon ages, and the original authors did interpret them to be stage 3, but as I showed, there is a large uncertainty in the actual age of those features. That brings us to the Larsemon Hills as we continue our clockwise journey around Antarctica. We're going to be looking at some isolation basins here. The Larsemon Hills have over 150 lakes and isolation basins of elevations up to about 115 meters. 7 of those lake basins and isolation basins have pre-LGM ages greater than 20,000 years. You can see the marine ones, those 3 of them have marine diatoms in the base of them that have also old radiocarbon ages. And you can see their elevations of 8, 10, and 5 meters. And then 4 more that have pre-LGM ages in the base of them, but no marine deposits at 15, 30, 65, and 85 meters. And then 2 of these also have 2 TL ages. Probably the best one of these isolation basins is Kirisej Pond, shown here in this photo by Dominic. It has a sill elevation of about 8 meters, and it has marine diatoms at the base. The original chronology found a till above those marine diatoms that had a TL age of 24 to 35,000 years old, and 24 to basically 43. So that would be the age of the till on top of that marine unit. The original radiocarbon ages were greater than 43,000, but they were revisited. This is always one of those things that kind of stinks. When you get more dates, it adds more confusion to your interpretations. They came up much younger, and it was originally interpreted as 5E, then they interpreted it as stage 3, and then in a recent review paper, they went back to stage 5E. So the other ones from the Larsemont Hills, other isolation basins and lakes have a highest marine at 10 meters, the lowest freshwater at 15 meters. So we know whatever high stand this was, we've constrained that elevation between 10 and 15 meters. The ages are consistently 20 to 30,000 years. 16 of them are 20 to 30, one TL age of 65 to 98. But that TL age was not directly tied to any of the 24 to 30. So once again, a very unsatisfying conclusion from the Larsemont Hills. We have a marine limit of 10 to 15 meters. The ages are not certain, and the original authors had interpreted it as LIG. That brings us to our last little area here, Cape Ross, in the Ross Sea, which has a series of raised beaches. And I will say, reading through all these, this is probably the strongest case for an LIG age. And so here we have raised beaches up to an elevation of about 34 meters on this little peninsula, about just north of McMurdo. They were originally thought to be Holocene until they were visited, and they returned pre-LGM radiocarbon ages. Now, within these beaches, and I think this is one of the points that Andrea made a little earlier, is it's really important to put in context the stratigraphy that might be able to tell you a little bit more. And so here, there are 3 distinct units within the raised beach. There's an upper unit of windblown sand, an upper reworked kind of, if it was a marine, we call it palimpsest, but sort of reworked upper unit to that beach, which has an abandoned rookery that dates to greater than 28,000 years old. Then there are 2 other units. The middle one is probably our best candidate for a potential LIG beach ridge. There are 6 radiocarbon ages from it, all at the older side of it. The 22,000-year-old age comes from an elephant seal, which oftentimes those can be left later on after after the beach was deposited, kind of like a rookery. And there was an Adelie bone within that deposit that the DNA mutation rates suggest is somewhere between 30 and 100,000 years old. The lower unit is cleaner, well-sorted sand matrix with several 5 ages you can see there, and an AAR that suggested 300 to 600,000 years old. And there's unconformities that separate those 3 different units. Now, Cape Ross has elevations from 23 to 34 meters. The mainland nearby, these beaches go up to about 31 meters. So although there are no Holocene dates on RSL on this exact peninsula, just to the east and to the west, we find the marine limits somewhere between 21 and 31 meters. So the summary for this, marine limit of about 34 meters. The ages are uncertain, but the original authors were very careful not to interpret them as a specific time, but just a pre-LGM high stand. And one thing I will also bring up, this isn't the Transantarctic Mountains, and there's no present indications of tectonic uplift. It is part of the rift. It is the flank of a rift basin, so it's not out of the question. So there's several other sites, but don't have much RSL information. There's some terrestrial limiting stuff in Queen Maud Land right up there. There's some marine limiting stuff where there's a radiocarbon age or pre-LGM age or maybe biostratigraphy, but it's in like 60 meters or 400 meters of water. So even though it's better indication biostratigraphically that it's an MIS 5E, it doesn't tell us much about sea level. So if we kind of look, one of the points I want to bring up is if we look at those different areas and we look at the difference between these pre-LGM beaches and the modern Holocene marine limit, they are not very different, okay? Okay, so that brings us to this question. Are they marine LIG or are they marine isotope stage 3? It's difficult to determine, as I've kind of drilled into your head already this afternoon. There have been other attempts to date it with other techniques, but they have been equally as fraught. And unfortunately, we have no corals within these deposits. So what I'm going to do is there was a study already from the Japanese group that said, okay, well, we know these are pre-LGM. What if they were stage 3 versus what if they were stage 5E? So from the stage 3, at first I thought there's no way that these could be stage 3. But there was a scenario where you can get a plausible scenario that would produce stage 3 sea levels higher or real close to present. And what they were able to do is if you take a pretty stiff Earth model, which isn't unreasonable for East Antarctica, considering that's the craton of Antarctica. They started with Pippa's ice sheet model for the LGM. The timing alone cannot do it. You have to do something to the ice load to be able to produce MIS-5E. And so if there was a larger than LGM ice, it doesn't have to be the entire ice sheet. It just has to be locally in that part of East Antarctica. And I will say that there are some indications that the LGM ice sheet was not particularly much larger in this sector of East Antarctica. So it's not an unreasonable solution to have a little bit larger of an ice sheet just over these parts of East Antarctica at maybe stage 4 or sometime prior than stage 3. That would make sea levels up higher during marine isotope stage 3. So what if we say that these RSL indicators are last interglacial? So I'm going to take a very simple one. I know there are more complicated ways, and we hope to maybe do this a little better. But we're going to use just a 1D symmetric model. Slightly different Earth model depending on which ice model we used. And we went with 4. 3 with no collapse, ice 6G, Glock 1D, that's Sarah's one that's tuned kind of for the British Isles, and the ANU 2017, and then 1 with a West Antarctic ice sheet collapse. And so let's run that at these 4 different locations across Antarctica and see what it means. So here they are. The one that you want your attention is the orange one. That's the one with the West Antarctic ice sheet collapse. So Livingston Island in the Antarctic Peninsula, Lutzow, Home Bay, Larsamon Hills, and then Cape Ross. And one thing we can see, the Livingston Island isn't very helpful. All scenarios put sea levels during 5E a little bit lower than what they are today. So that, I guess, that it makes us feel better that we don't know much about that tectonic correction, right? In Lutzow, Home Bay, and Larsamon Hills, we get sea levels during 5E that were higher than today, about 10 to 15 meters, while the ones without collapse produce sea levels below present. And what's interesting is that's about what the elevation is of that pre-LGM ice sheet. The one real telling one is the one at Cape Ross, where if we didn't have a collapse of the West Antarctic ice sheet, we have sea levels below present. The only scenario where we get it higher, and a little bit higher than the Holocene limit, is that if we have a West Antarctic ice sheet collapse. So I'm going to help you out, Alessio, and help you finish on time, since we're going to start a little late. So I zoomed in here, Livingston Island, below present. I think I already went over those scenarios. So several pre-LGM sea level indicators are found throughout Antarctica. Just it's very unsatisfying that we don't have a good way to date those yet. And their age is still poorly constrained. Are they marine isotope stage 3 or are they LIG? If the Cape Ross pre-LGM beaches date to the LIG, it may suggest that West Antarctica ice sheet collapse during the LIG. There is a solution consistent with our observations. That solution is also consistent at our other two locations where we find these pre-LGM beaches. So with that, I'd like to thank the people that helped us in some of our campaigns to Antarctica and the no longer existing National Science Foundation Office of Polar Programs. So thank you.